In this video, we're just going to introduce some single-stage op-amp circuits other than the folded cascode. One technique that's sometimes used in single-stage amplifiers to increase their gain is to make use of current mirrors with an enhanced output impedance. Remember that single-stage op-amps and CMOS are usually constructed by using the small signal transconductance of a diff pair transistor and multiplying the resulting small signal current by a relatively large small signal impedance. So it's of great interest to look for techniques for designing CMOS current mirror circuits that have a very high output resistance. So shown here is a simple current mirror between Q2 and Q3 with what looks like a cascode transistor Q1. Except normally the gate of the cascode transistor would just be connected to a fixed DC bias, but instead there's a feedback circuit with an amplifier A connected driving the gate of Q1. So assuming this mini little feedback loop here is stable, then we see that we expect a virtual short circuit between the input terminals of the amplifier A, and therefore we would expect that the drain of Q2 would be approximately equal to the bias voltage applied here. So V bias would be chosen just above the V effective of transistor Q2 in order to keep it in active mode. Then the amplifier is going to generate whatever gate voltage is required to try to clamp, if you like, really hold that voltage there constant at V bias and not let it move around at all. And so by doing so, it really limits the channel length modulation that arises in Q2 and therefore keeps its drain current very, very constant, even in the presence of voltage swing at the drain of Q1. In a sense, Q2 is shielded from that, not just by Q1, but is further enhanced by the gain of the amplifier A. So indeed, if you do a more detailed small signal analysis of this stage, you would find that the small signal output resistance looking into the drain of Q1 is an expression that looks pretty much like the cascode output resistance, GM1 RDS1 times RDS2, further multiplied by the gain of the amplifier A. In fact, 1 plus the gain of the amplifier A. So this is a sort of a consequence of the feedback around this loop. You see this familiar term of 1 plus the loop gain around this loop here. Q1, as far as this mini little feedback loop goes, is acting as a source follower, so has a gain close to unity. So this loop gain here is approximately equal to A, and indeed you see the output impedance here is boosted by 1 plus A. Now, when using this technique, so it's a technique that can be used to achieve a very high output resistance for this current mirror without, in fact, impacting the swing you have available here at Vout. You can still allow for an output swing on the voltage Vout that's pretty much the same as what you could have from a simple cascode current mirror, but now with an enhanced output impedance. The drawbacks here is that you've got an extra amplifier A that's going to consume some extra power. And you've also got to make sure this feedback loop is stable. But so typically this amplifier is fairly simple, a simple amplifier, so as not to complicate the stability of this feedback loop here. Using a simple amplifier for A also helps keep its power consumption down. And when this technique is used for a cascode amplifier instead of a cascode current mirror, it's referred to as gain boosting, because instead of having the traditional cascode stage gain GM times the output impedance of a cascode stage, now we've got GM times the output impedance of a cascode stage times 1 plus A. So you've really boosted the gain of this cascode stage by the gain of this amplifier A. It's kind of an interesting technique because rather than putting this amplifier in series with the Cascode stage, that would also increase the gain by a multiplicative factor of A. But instead of doing that, you kind of embed A right here in this little feedback loop, and you get the same improvement in gain, but you may get a benefit in overall power consumption, because in this circumstance, the amplifier A only has to drive the gate of Q1, whereas if you tried to connect or design an amplifier here to be connected in series with the signal path, now it needs to drive uh, potentially a larger capacitive load, so it might require more power consumption. Now, to realize the full benefit of gain boosting, you of course need a very high output impedance active load, I bias here as well. So in general, if you use gain boosting for the Cascode amplifier, you're going to also want to use similar out and output impedance enhancement amplifier for this current source, I biased. In many examples of gain boosting circuits, a full op amp here is not used. It could be a very simple actively loaded diff pair, or even just a simple common source stage. The gain, need not be so high. Any gain in this feedback loop, A, just helps boost up the gain of the signal path here. So gain boosting can be used in a single stage amplifier to realize even higher gain than what's normally achievable from a single stage. So for example, here you've got a PMOS input folded Cascode amplifier where gain boosting is used extensively. First of all, for the current sources here in the output stage, their output impedance is enhanced by these two amplifiers. And for the folded Cascode transistors, M4P and M4N, they also have gain boosting amplifiers here. So there's gain boosting on both sides of the op amp, enhancing the DC gain of the amplifier significantly. Each of these gain boosters is itself, in this particular example, a folded Cascode. Now you'll notice that the transistors that are driving the gate of the PMOS, the amplifiers driving the gates of the PMOS Cascode devices, have to accept as inputs relatively high voltages here. So therefore, these two amplifiers have to have NMOS input pairs, whereas the amplifiers, the gain boosting amplifiers driving the NMOS Cascode transistors, accept as their inputs relatively low voltages. So these two require PMOS input stage. Another style of CMOS single stage amplifier is the so-called current mirror op amp. And in order to illustrate it simply, it's useful to have a simplified schematic symbol for an idealized current mirror. So whenever you see this symbol here in the coming slides, you'll know that this represents a CMOS current mirror. It may either be a simple current mirror or a Cascode current mirror. It doesn't really matter for sort of a very high level understanding of how the circuit's working. This connection here denotes where the current's ultimately coming from. So with the arrow pointing up, it suggests that the current's coming from positive supply, and the arrow pointing the arrowhead here at the output indicates which side of the current mirror is the input. So if this is a simple current mirror, this symbol here is shorthand for a PMOS current mirror connected to the positive supply, and with the left side node being the input to the current mirror. If there's an annotation on the symbol like this, identifying a ratio of 1 to k in this case, that is the ratio of the sizes of the devices in the current mirror. So it means that this transistor on the right has a W over L ratio k times larger than the one on the left. Therefore, currents here are mirrored here with a gain of k. So with that understanding, here's an idealized schematic of the current mirror op amp. So this is a single stage op amp with input differential pair Q1 and Q2. And the input differential signal therefore gives rise to two small signal currents, GM1 times V in over 2 this way, and GM1 V in over 2 running that way. So these are the small signal currents. Obviously, they're superimposed on the bias currents that are determined by the tail current source here. Now, these small signal currents are inputs to the current mirrors here and here. So this drain current, small signal drain current from Q2 is mirrored over to here, GM1 V in over 2, and the small signal drain current of Q1 is mirrored over here, but this one sees a gain of K. So over here we've got K, GM1 V in over 2. Now there's a final mirroring that occurs over here. This current is input to an NMOS current mirror with a gain of K, and so we've got a small signal current over here that's GM1 V in over 2 times K. So coming into this node here, we've got two small signal currents, both of them equal to GM1 V in over 2K. So we've got a total current coming into that, small signal current coming into that node of GM1 V in times K. So in effect, this single stage amplifier operates by accepting a differential input V in and exposing it to transconductance GM that's equal to K times GM1. And then that current is pushed into this output node here where it sees the output resistance of the small signal output resistance of the op amp and of course any load cap CL, giving rise to the amplifier's single time constant response. So it's a single stage amplifier because if you consider the circuit node by node, you will see all nodes except for the output node are connected to the input of a current mirror. And the input of a current mirror sees a small signal resistance of 1 over GM. So the only node here with a high DC small signal impedance or small signal resistance is the output node here. The output node sees only the outputs of two current mirrors. So R out can be made large. Those current mirrors can be Cascode current mirrors or gain boosted Cascodes even to realize higher output resistance and therefore get higher gain. But the interesting thing here is, again, it's still a single stage amplifier. So as with all single stage amplifiers, we expect the unity gain frequency of the amplifier to be its capital GM over CL. But with the folded cascode, the capital GM was just equal to the small signal transconductance of the input pair, whereas here we've got this additional term K, which is the gain of these current mirrors. So in effect, it's sort of an extra degree of freedom we have in setting the transconductance of this amplifier, and it shows up here in the unity gain frequency expression. So whereas with the folded cascode, if we wanted to increase the unity gain frequency for a fixed load cap, really all we could do is try and increase the input transconductance GM1 as much as we could. Here, instead, we can increase the current mirror ratio K. In fact, if you consider the case where you have to fit the whole op amp within a fixed power budget. So you have a fixed total bias current, I total, that you can spend on all these current branches combined, it turns out that rather than pumping a lot of current into the input pair transistors, which is what you would do with the folded Cascode to maximize its transconductance, instead you would actually spend more of the current on the output branch, because by doing so you can increase K and thereby get a higher unity gain frequency, omega TA. And here we're again assuming that the amplifier is essentially just has a single time constant response. It's completely dominated by the load cap CL. The picture gets more complicated if we have second poles that limit our unity gain frequency. And we have to compensate the loop to actually lower the unity gain frequency because of those second poles. So again, if we recognize that the bias current flowing in each of these paths can be written in terms of IB, the tail current for the diff pair Q1 and Q2, right? Here we've got half of IB2 on each side of the diff pair. Here we've got IB over 2 times K. Here we've got another IB over 2, and then and then that gets mirrored by K to give rise to the K times IB over 2. So in total, if we consider all the currents flowing from the positive to the negative supply, or from the positive supply to ground, we've got IB flowing in the input stage diff pair, and then we've got a K plus 1 over 2 IB flowing in the output stage. So we can rearrange this into an expression for IB in terms of I total, and IB is then in turn related to the GM of Q1 and Q2 and its V effective. And combining all those expressions gives us this expression here, and this is the unity gain frequency of the amplifier. Note the subscript A here. If this op-amp is used in a feedback loop, of course, the unity gain frequency of the feedback loop would be also dependent on the feedback network. But this expression is useful in highlighting design trade-offs that are available to us. So as before, if we have a purely first order response from the circuit, that is, we can neglect the second and higher order poles introduced by internal nodes in the circuit, and we have a completely dominant output pole due to load cap CL. This would be the case if we have a quite large load cap to drive CL, large in particular by comparison with the total current we have available to spend. So in that case, we're totally dominated by the output pole. So in such a case, the bandwidth of the amplifier is given by this expression. And if we want to design the amplifier to maximize the bandwidth with this power constraint, our total current consumption limited to I total, there's not too much we can do. I mean, more power would allow us to increase the unity gain frequency, but if we don't have that option open to us, then as was the case in the folded Cascode op-amp, the other thing we can do is ensure that we're biased with a low value of V effective 1 and 2. Now, embedded in the derivation of this expression is a square law assumption for Q1 and Q2, because we've assumed GM1 and 2 equals 2 ID1 over V effective 1. So, this suggests that we would want to maximize the bandwidth under these conditions. We would minimize V effective 1, which really means pushing it to the verge of subthreshold operation, beyond which we get diminishing returns. But again, the other interesting conclusion that comes forward here is that increasing K actually increases this term here. So higher values of K keeping all else equal, would actually give us a higher bandwidth. So again, keeping in mind that if we've got a fixed I total, increasing K means that we're increasing the current in this output branch here. So that has to come at the expense of current in the input stage. So it's quite interesting. It's exactly opposite the folded cascode stage where, um, again, to maximize the unity gain frequency, assuming a first order model, we would pump more current into the input pair transistors. Here we'd actually pump less. We'd pump more current into the output stage transistors because, again, that would increase our K factor. Now there's a point of diminishing returns here. Increasing K, eventually this term will approach unity, and there's not much point increasing K much beyond that, but you might get current mirror gains K up to say 4, or not is not unreasonable. Let's also briefly consider the slew rate performance of the current mirror op amp. Let's imagine that an input step arises that is large enough, positive input step that's large enough to completely switch the input pair so that all current flows through Q1 and Q2 is completely off. So in this case, the current IB flows through Q1. That gets mirrored by a factor of K. So we've got K times IB flowing here. At the same time, there's no current flowing in this branch. That gets mirrored over here, zero current flowing here, and therefore zero current flowing here. So all of the current K times IB is delivered to the load cap CL, which causes the output voltage to increase with a slope of K IB over CL. And that is indeed the slew rate of this op amp. Now we could do a similar analysis for a large negative transient arising at the differential input, and that would give rise to the exact same slew rate in the negative direction. So you can leave that for an exercise for you, but in either case, the slew rate is K times IB divided by CL. So again, in general, in single stage op amp design, there's two possible scenarios you could face. One is where you're constrained to very low power compared to the load cap that you're trying to drive. In that case, you're most likely completely dominated by the pole at the output node. And so really there, generally what you want to do is use what little current you have budgeted for the op amp to maximize uppercase GM. Now, in the case of the folded cascode op amp, that means maximizing the small signal transconductance of the input pair transistors. In the case of the current mirror op amp, that means maximizing the current mirror ratio K. But in either case, maximizing capital GM is what's going to give you the highest unity gain frequency. And since you're totally dominated by the output pole, you don't really have to worry about compensation or phase margin because you're going to have a phase margin close to 90 degrees in any case because of that hugely dominant output pole. But the other scenario is where you're actually trying to operate at a very high bandwidth and you have a little bit more current budget available to you and or the load cap is not so large. So in this case, if you just max out uppercase GM here, you're going to push the unity gain frequency so high that you start running into the second and higher order pole frequencies due to internal nodes in the op amp circuit, and therefore you're going to start having phase margin troubles. So in those cases, again, your bandwidth, the op amp will require some compensation, and the ultimate bandwidth you achieve will therefore be limited by the second and higher order poles because you're going to have a unity gain frequency somewhat below those second and higher order poles to ensure you achieve whatever phase margin you're targeting. So again, as before, the second and higher order poles of this current mirror op amp are of interest. Here's a more detailed schematic of a current mirror op amp showing the details of the current mirrors themselves. In this case, they're Cascode current mirrors, which you would expect would be needed in order to achieve a high enough DC gain, given that it's just a single stage op amp. And so looking at this more detailed schematic, it's evident that the second pole is likely arising at this node here, identified by the red dot. The reason being the small signal resistance at this node here is approximately 1 over GM5 due to the diode connection around this Cascode current mirror here. And remember, Q5 is only biased with half of IB, but also connected at this node is the gate source capacitance of Q8, which is K times larger than Q5. So again, if the current mirror here has a gain of 2 or more, then it's got a relatively large CGS connected at this red node, but a smaller transistor is what's giving rise to the 1 over GM. So the RC time, the small signal RC time constant here is GM5 times CGS8, which is K times bigger than CGS5. So that's that, and the same is not true here. Here, the current mirror ratio is only 1 to 1, so CGS 7 is not as large as CGS 8, and yeah, and then over here, you might say you've got a similar looking scenario, but in most technologies, the NMOS transistors will exhibit a higher carrier mobility, and therefore we might expect the GM of Q13 to be larger than the GM of Q5. So, again, for all these generalizations that we make here, there's always going to be exceptions to these rules. So it's good to understand the underlying premises. But again, the second pole, subject to the assumptions we talked about, the second pole frequency is likely to arise here. So if we have an op amp that is limited by the second pole frequency, we may want to do whatever we can by design to maximize that pole frequency. What can we do? Well, again, what we would like to do is increase GM5 to make the time, to decrease the time constant, the small signal time constant associated with this node. Increasing GM5 means increasing its bias current, determined by IB. If we increase the bias current IB but keep the total power budget the same, that's going to mean a decrease in K. So again, it's the exact opposite trade-off we saw for the folded Cascode op-amp. When the second pole is dominant here in the current mirror op-amp, we actually want to push more current in the input pair and less current in the output pair.